Ladies and gentlemen, let's continue with chapter 4 in the textbook of Cengel and Ghajar. May I also ask the gentleman there at the back if you would be so kind to close the doors for us? I will appreciate that. So we are busy with chapter 4 on transient heat conduction. Transient means temperatures changes as a function of time. And the chapter is divided into 4 main parts. The first one is the lumped system analysis method that we've already done, and I've specifically showed you what are the limitations for the lumped system approach. Then the next approach was to look at the transient heat conduction in large plane walls, long cylinders and spheres. So 3 of the most common geometries that exists. And the third part would be transient heat conduction in semi-infinite solids. Maybe today we will just start with it. And then the last part would be transient heat conduction in multidimensional systems. So in the previous lecture, I've actually completed all the theory on the transient heat conduction in large plane walls, in cylinders and spheres. And there wasn't enough time to do an example. I've specifically showed you table 4.1, the fine print underneath it. There it is actually on the board, table 4.1. We'll come back later to it. And then there were very specific solutions or special cases for that solution. The solution is an infinite series, and from previous work, and if you've worked out many examples, it can be found that if tau is larger than 0.2, then you only have to use the first term. And the first term, of course, first term approach can be written in simpler equations than that one, and it's given in your textbook, and it can also be given for the special case at the center. Together with that were some graphical solutions also for the plane wall, the cylinder, and the sphere, which are called Heisler charts. And on it, you can also get typically the non-dimensionalized temperature gradient as a function of the Biot number and the specific position where you want the solution. So there's nothing better to illustrate the theory than doing an example. So let's do an example where we're going to apply what we've learned with the previous lecture. And I don't know how many of you look at these TV series like NCIS, etc. But it is one of the questions always is, if there's a dead body, then the question is, well, how long ago did the person pass away, or was he or her killed, isn't it? Okay, so let's look at this case and see if we can develop a solution for that. So the dead body, after looking at it, can be approximated as a person with approximately a length of 1.7 meters and average diameter of about 300 millimeters. Okay, so we are going to assume it is a cylinder. Diameter 300 millimeters and length 1.7 meters. And the room in which the person was found was at environment temperature, an average one of approximately 20 degrees Celsius, and the heat transfer coefficient was estimated to be approximately 8 watts per square meter degree Celsius, which means that most probably there wasn't a fan in the room, there wasn't air conditioning, it was just natural convection. And the temperature in the center were determined with a thermometer. Usually they take a thermometer and they would put it and they would measure the temperature in the liver, which is approximately at the center of the dead body. Okay, so the temperature at the center was determined to be 25 degrees Celsius. And that was at 1700 hours. So at 1700 hours, they measured the temperature of the dead body, and it was 25 degrees Celsius. So the question is, how many hours ago did the person pass away, or was he or she killed? And what we're going to do is we're going to actually use the lump system approach and the more accurate approach so that we can compare the two and hopefully make it easier for you in future to decide which approach you can use. Now, if you think back of the theory that we've done in terms of the cylinder, the exact solution for the cylinder, as well as for the lump system, you'll see that there are certain properties which are always required, like the density of the body, the CP value, the K value, etc. Now those values, you're going to have to go and get it in many cases in the tests and exams. So again, I've mentioned how important it is for you to get to know your textbook. If you've done it many, many times, you will know that you'll be able to get the results in table A9. So if you go and look in table A9, you will actually get the properties for water. Now why am I going to use the properties for water? Because 80% of a human being is water, and you will see human flesh, the properties of it is not in the textbook. So it is an assumption, a first order assumption that I'm going to make, because I do not have all the information. You can go and Google and get the more accurate values if you want. Okay. And for those of you who have your textbook here, it would be a good thing if you flip it open and you go and look in table A9. And immediately you will see, oh, there's a problem. And what is the problem? You will see that all the properties is dependent on temperature. Okay. So the first question is, if you now select the properties, must you select the properties as 25 degrees Celsius, or must you select it at another temperature? For most of us, if you're healthy and living, your body temperature should be 37. So the properties somewhere between 37 and 25 will most probably be the properties that you will have to use. You're going to see in many cases that we are going to refer to this temperature as the bulk temperature. So the bulk temperature is considered as typically the temperature at the beginning and the temperature at the end, which is 37 plus 25 divided by 2. Why 37? Because that's typically the temperature of the human body if you're normal, if you're healthy and alive. Okay, so it gives us a bulk temperature of 31 degrees Celsius, and therefore it means that you need to get the properties in the textbook at 31 degrees Celsius. Immediately you will see, you will have to do linear interpolation. I'm usually too lazy for that. I will select the closest one and I will select 30. And you can also do that in the tests and exams. I know by now that you know how to do linear interpolation. There will be cases, however, where you will have to do linear interpolation. And that will be where between the two, so if you go and look at the tables, then most probably the properties are there for 30 and for 40. And you will see that in most cases the properties are quite close to each other. Okay. So for that reason, I'm going to select the values at 30. But there might be cases where there's a huge difference between the values. And then in those cases, then you have to use your judgment and you have to do linear interpolation. But in general, I will not expect that of you. Right, so let's go and look at a temperature of about 30 degrees Celsius. What are the property values? So K is equal to 0.617, and the units in watts per meter Kelvin, the thermal conductivity. The density of water is 1,000 kilograms per cubic meters at that temperature. And the CP value is equal to 4178 joules per kilogram degrees Celsius. You're going to use these values a lot, the values for water and air, so it would be good that you start developing a feeling for it. You should know approximately what they are. And then we can also go and calculate alpha. I cannot remember if it is given in the textbook, but it is, in some cases, it will be. It is equal to K divided by rho Cp, and that is equal to 1.477 multiplied by 10 to the minus 7 meters square per second. Okay. So now we have all the properties that we need. So let's start by using the lump system approach. Now, if you have done many lumped system problems, then most probably you will already know that this is not a good approach to follow, because we've set the lump system approach typically for Biot numbers, I think less than 0.1 or something like that, and small in terms of geometry, thermal conductivity high, small bodies. Most probably that one is not going to do it, but let's say we are not experienced and we want to test the water and we want to see what is going to happen. So that is what we're going to do. So with a lump system, we calculate the characteristic length as the volume divided by the surface area. Okay. Now the volume of the body is equal to pi divided by 4 multiplied by the diameter multiplied by the length. The volume. Okay. The volume, pi divided by 4, d squared, it would be that surface area, multiplied by the length, and that would give us the volume. The surface area would be pi dl. Pi dl would give us that surface area. But now we also have to take into consideration that surface area and that surface area there. You agree? So it is pi dl plus 2 times pi divided by 4 d squared. Okay. Now I'm not going to bore you by putting in the diameter and the length. There it is. The diameter is 0.3, the length is equal to 1.7. You can go and do the calculation, and the characteristic length worked out as 0.0689 meters. Now, because we're going to use it later on, I'm also going to just write down the surface area, which would be that term there at the bottom, and that is equal to 1.744 square meters, and the volume as 0.1202 cubic meters. Right, let's calculate the Biot number. The Biot number is now equal to the heat transfer coefficient multiplied by the characteristic length divided by the thermal conductivity K. The heat transfer coefficient is equal to 8. The characteristic length is equal to 0.0689 divided by the thermal conductivity 0.617, and that gives a Biot number of 0.89. Okay, 0.89. Okay, so this immediately tells us lump system not appropriate. You shouldn't use a lump system approach just because of the Biot number. But let's go and check it in any case. See what the answer is. So with the lump system approach, says that the non-dimensionalized temperature, which is equal to the temperature minus T infinite divided by Ti minus T infinite is equal to E to the minus BT. Where B is equal to the heat transfer coefficient multiplied by the surface area divided by rho, the volume, and Cp. Again, I'm not going to put in all the values. The heat transfer coefficient is 8. Okay. The surface area, there it is 1.744. The density is 1,000. The volume, 0.1202. And CP is equal to 4178. Everybody understands that? Very simple. You happy with that? Okay. So, if you go and calculate it, then the value of B is equal to 2.778 multiplied by 10 to the minus 5 per second. That's the value of B. Okay. Let's do the substitution in this equation. Okay. The temperature at a certain period of time. That will be when the body is discovered or when the temperature is measured. Okay, so we want to measure the temperature and determine how long ago was the person killed. Okay. So the temperature at T is equal to 25. Okay, the temperature at time T. The original temperature was 37. The initial temperature, the temperature is 25, the environment temperature is 20. Okay. The initial temperature was 37 minus the environment temperature is 20. Okay. And that ratio we are going to use later on is actually equal to 0.8824. Okay. So remember what happened now as temperature as a function of time. So the original temperature was 37. Okay. And the body, and we are here now at 25. So that is the temperature as a function of time. And we want to determine how long ago was a body at 37 degrees Celsius. Okay. So if we now look at equation 1, then this non-dimensionalized temperature, that value there, is equal to 0.8824, is equal to E minus B, and B is equal to 2.778 multiplied by 10 to the minus 5 multiplied by T, and the only unknown is T, and the result of T is equal to 4,506 seconds, which means it is 1.25 hours ago. So 1.25 hours ago, the body temperature was equal to 37. Question?
So the ratio there, wasn't it supposed to be 0.29? Or is there something?
He says that this ratio should be equal to 0.2 something. You can just check. I've got it as that, but unfortunately, if you're correct, it wouldn't work for me to redo everything. Just go and recalculate all the values. Okay. Am I right with this? 25 minus 20, 37 minus 20, something like that. Okay. Okay. So just look at the principle at this stage. Okay, so the time is 1.25 hours ago, which means that if the body was discovered at 1700 hours, we can just subtract 1.25 hours from 1700 hours to determine how long ago was the body at 37 degrees Celsius. Okay. The other approach, remember, with the previous lecture, when we've defined the non-dimensionalized variables, like the non-dimensionalized Fourier number and temperature and Biot number, we said that this equation, equation 1, can also be written in a non-dimensionalized format as theta is equal to minus the Biot number multiplied by the Fourier number. Where, of course, this is the non-dimensionalized temperature. It is that ratio there. And most probably you're correct, and I did make a mistake when I calculated it. So 0.8824 is equal to E to minus the Biot number, and the Biot number is 0.89. multiplied by the Fourier number, and you can solve the Fourier number as 0.1407. But the Fourier number is also equal to alpha t divided by the characteristic length square. Okay, you've got the Fourier number, 0.1407. You've got alpha, you've got the non-characteristic length. So if you calculate it again, it should give you the same answer, 4,506 seconds ago. Okay. Any questions on the dead body problem if you use a lump system approach? You happy with that? Okay. Now, if you can take a look at table 4.2, Tamarin, if you can focus on that for us. Table 4.2, that was the summary of all three the solutions. We've just looked at this, how do you solve, or in the textbook is only given the one for the plane wall. But you can also do it for the other two, and that is the solution. Then we've said that if tau is larger than 0.2, then you only have to do the first term, which means you only have to solve A1 and tau 1. And that is the solution for those three cases. A general solution, those three equations at the top, and then underneath it, the special cases where r is equal to 0 or x is equal to 0, which means it is on the center. So taking that into consideration, it looks quite complicated, but once you start looking for it, or once you've done quite a number of problems, you'll see that in general, you can start solving that if you've got the Biot number. Then you can get very easily, and I will show you just now all the other variables, and then at the end the equation is actually very simple. So let's look at the case for a cylinder. Okay. So for a cylinder, we have that the Biot number is equal to 1.944. Oh, sorry, 0.89. Okay, Biot number, there it is, 0.89. And then that Biot number is part of the eigenvalues that needs to be solved, and the results are given in table 4.1. So if you look in table 4.1, you'll see that there's a solution for, look for the cursor, there's a plane wall one, there's a cylinder, and there's a sphere, and there are the Biot numbers. So if you go and look at the Biot number, the right Biot number, you can get the value of lambda 1 and A1. Most probably it is too small for you, so it would be better if you look in your own textbook. So for that case, you will see that lambda 1 is equal to 1.2048, and A1 is equal to 1.1902. And then the equations that I've showed you just now, if I can go back to them quickly. Tamarin, if you can just show them again. Remember, they are the special cases if tau is larger than 0.2. But tau is the non-dimensionalized temperature, which we actually do not have. That is the one that we want to solve. So what we're going to do is we're going to assume it is larger than 0.2. And then we will check the solution and see if it is. So assume it is larger than 0.2. And if that is the case, then the non-dimensionalized temperature, 0, it means at the center. At the center, if we just look at this, okay, that is R. So that is where R is equal to 0 in the center of the body. That was where that temperature was measured, 25 degrees. So the non-dimensionalized temperature for the cylinder is equal to T0 minus T infinite, Ti minus T infinite, which is then equal to A1 e to the minus lambda 1 square multiplied by tau, and that is equation 4.12. 27 in your textbook. It's also given, I've showed it to you just now. Okay. Therefore, it is actually now very easy to solve it. The temperature at the center is 25 minus the environment temperature is 20. Ti is 37. T infinite, the environment temperature is 20, is equal to A1, and A1, there it is, equal to 1.1902 e to the minus lambda, and lambda is equal to 1.2048 square multiplied by tau. And now tau is equal to 0.963. Okay. And that is equal to alpha t divided by LC squared. Alpha t is equal to, alpha is equal to 1.477 multiplied by 10 to the minus 7 multiplied by t divided by the characteristic length is equal to 0.0689 squared, and from that we can solve that the time is equal to 146,772 seconds, and that is 41 hours ago. 3 days. I'm going to get to you just now. Are all of you happy with the principle I've used to solve the problem? It's easy, isn't it? Okay, you are smiling. Question? Yes, yes. Thank you very much. So this is all wrong. I've warned you against it. Why? Because this Biot number is based on the characteristic length, and it shouldn't be. The definition for the Biot number for the lump system approach, where we use this definition, is a unique one, and in general we do not use it. So if we go back again to table 4.1, I've warned you against the fine print. If you look underneath it, what does it say? The Biot number, I think it is too far for many of you, says that the Biot number is equal to HL divided by K, that's obviously for the plane wall, or HR0 divided by K. Okay, which means that the answer is totally wrong. Okay, so let's go and look how it should have been done. You should have calculated the Biot number as HR0 divided by K. The heat transfer coefficient is equal to 8, and now the radius is 0.15 meters. Divided by the thermal conductivity is 0.617, and now my Biot number is equal to 1.944. If the Biot number is equal to 1.944, again, if you now go and look at the tables, I do not expect of you to go and do linear interpolation at 1.944. Let me see if we can get it quickly. There it is. You'll see there's a solution for 1 and there's a solution for 2. So in the test and exam, if you use 2, I'll be happy with it. If you go and do linear interpolation, then the correct values, I think, is equal to 1.5995, or maybe I've used the values at 2, I cannot remember, and A1 is equal to 1.3384. And now, going back to the solution for the cylinder is equal to temperature at the center minus the environment temperature, the initial temperature minus the environment temperature is equal to A1 e to the minus lambda 1 square multiplied by tau. Temperature at time t is 25. It didn't cool down to 20. It's on its way. 25 minus 20. 37 minus 20 is equal to A1 is now equal to 1.5995 e to the minus lambda 1, and lambda 1 is, A1 is equal to 1.3384, is equal to e to the minus lambda 1.5995 multiplied by tau. Okay. Now you can go and solve tau. And tau was equal to 0.6466. So the one-term approach is therefore valid. Okay, so fortunately, tau is larger than 0.2. Therefore, we only have to use the one-term approach. And tau is equal to alpha t divided by r0 squared, not the characteristic length. Okay. And tau is equal to 0.6466, is equal to alpha, is equal to 1.477 multiplied by 10 to the minus 7 multiplied by t divided by R0, and R0 is 0.15 squared. The result is that the time is equal to, and look at the difference, 98,517 seconds, and that is 27.37 hours ago. Okay. 27.37 hours ago. So coming back to what the problem was we had a human being that was alive, and then there was a murder, and the body was in an environment where the temperature is 20. It was cooling down, and it was discovered at a certain time, 1700 hours, when the temperature was measured as 25. So this time, delta t there is equal to 27.37 hours ago. Any questions, ladies and gentlemen? Nothing. Now remember, we are still busy with the first order approximation. The first order approximation in terms of the tools available to us. So in terms of the tools available to us, we can see the lump system approach is not going to work. Then we're going to say, well, let's assume it is a cylinder. And what was wrong with our assumption? Our assumption was, of course, that this dead body, that the heat transfer rate was only in the r direction. So it's only in one dimension. We did not take into consideration the heat transfer rate from that surface there and from the bottom of the feet. Okay. But that we will do later on when we get to the full three-dimensional body. There's a question. I beg your pardon?
Why did we consider the surface area?
Why did we consider the surface area? Okay. Remember, okay, so the question is, why did we consider the surface area? And I think you're referring to specific this part you saw, this part. Remember, with a lumped system, we've said any body can be an arbitrary body with a certain volume and a certain surface area. So there it was taken into consideration. However, it was not taken into consideration with the cylinder. With the derivation of the cylinder, just like with a plane wall, we've said to solve the equations. Now remember, to solve the equations, we've said that the heat transfer rate is only in one direction, and that is why the solution is only actually valid for a very long cylinder. The longer the cylinder will get, the less. I mean, let's suppose this cylinder was very, very, very long. Okay. The longer it gets, the smaller this effect and that effect will be in terms of the total area. Okay, so that's why it is valid for a long cylinder. Remember, we're on our way, where later on you'll be able to take that into consideration. Not yet, but we're on our way. Why did we? Sorry?
Why did we take the average of temperatures?
Why did we take that?
Yeah, why not just use 25 degrees?
Okay, sorry, I couldn't get the question. Why didn't we?
Why do we take the average of the temperature?
The average. Oh, okay. Right, yes. Okay. So the question was, why did we take the average of 25 and 37 in getting the properties? Okay. So what we did is we said that the temperature is approximately 31, the average temperature, and at that temperature we did go and get the properties. Correct, that's an assumption that was made. So again, remember, with the lump system, it was an assumption, it was assumed that the thermal conductivity stays constant, and then also to solve the plane wall problem is already complicated. If you go and take into consideration that the thermal properties varies, then you'll not be able to solve it analytically. You'll have to solve it numerically. However, just go and check, for example, and see what are the properties at 37 and what are the properties at 25, all three of them, and you will see that they differ with a few percent, which means that it is not going to make that much of a difference. Okay. Question there at the back?
So why do we take R0 as 0.15?
Yes, okay, R0, it is, in terms of the analytical solutions, what makes it easier is that typically there, you'll see everywhere where the solutions were derived, okay? So I don't know if you can see there in the sketch, but for the cylinder, it's very important to take into consideration the coordinates, and you'll specifically see in the last part of the chapter. So there you will see R0 is that distance there, which is the half of 300, it's 150 millimeters.
It says 500.
Sorry, 300, yeah. Yeah, so sorry, it's my handwriting. As I said, there's a difference between what I mean and what I write and what I say sometimes. Okay. No more questions? Okay. There's another approach that we can follow, but there's another question. Yes?
That type makes sense though, because it's my understanding, if you leave a glass of water in a room, its temperature changes quicker than just 37 hours. It's way faster than that. And we approximated the dead body with the properties of water. My question is, does that answer make sense though?
That answer would not be that inaccurate. Okay. So the question was, does this answer make sense? My answer is yes. In terms of what we've done so far, it would make the most sense. But wait for the last part. Because with the last part, we can take into consideration this part and that part also. Okay? So just be a little bit more patient.
That's only valid if it only leaves the body through the lateral path.
That is only valid if?
If the heat only leaves the body through the lateral path and we omit the ends of the system.
That's right.
Okay.
That's right. Because it is an assumption that was made. When we solved, firstly, the the large plane wall. Again, it was a wall which was considered as very long. So this distance is very long in comparison with this. And therefore it was a good assumption to say that the heat transfer rate is in one dimension only. So when we've considered the energy equation, we've said heat transfer rate is in the x direction. We didn't do it for the cylindrical and the spherical case because it's more complicated and because we don't have time. But for this case, the heat transfer rate is in the r direction only. However, in the case of the sphere, it is exactly correct because the r direction is actually in 3 dimensions. Okay, right. Now, there's another approach that can be followed, and that is by using the Heisler charts. Okay, we've also looked at that. So let's look at the case if we actually want to get what is called a graphical solution. Now with that, you have to refer to figure 4.18. And Tamron, if you can zoom in on that for us. So there's figure 4.18. And again, take note of the sketch there. It gives you everything that you want. It tells you exactly how you should calculate the Biot number, the non-dimensionalized time, in terms of that geometries. Now it will most probably be very small for you to see, quite sure. But what you will see in principle, we've got the non-dimensionalized time at the center. Okay? The non-dimensionalized time at the center. Okay, the non-dimensionalized time at the center means it is the temperature at the center, T0, minus T infinite, divided by Ti minus T infinite. And it's the same as that we have calculated here. And I hope I didn't make an error, but it should be 25 minus 20 divided by 37 minus 20, and the non-dimensionalized time should be equal to 0.8824. So we know that this value is 0.884, the non-dimensionalized temperature. And here are lines of 1 divided by the Biot number. Okay. Okay. And the Biot number is equal to 1.944. Okay. So it is equal to 1 divided by 1.944, and that would be approximately 0.5. Okay. Thus, it means that we need to go and look for the Biot number, 1 divided by the Biot number, which is equal to 0.5. Let's suppose it is that line there. Oops. Excuse me. You can't see it very well, but if you do that, okay, then you'll get the non-dimensionalized time. And look on the graph and see if you can do that. Okay. So 1 divided by the Biot number is approximately that line of 0.5. And then you'll see the non-dimensionalized temperature, is 0.8. So it's very close there. Okay. So if your eyes are as good as mine, then you will see that this value is exactly 0.6. What was it? 0.6466. Okay. Okay. So you will see on these charts, and specifically in this case, the lines are so close to each other, there's no ways in which you can see properly. But in some cases, it might not be. And then you can actually get the value very accurately. So, if you now have, from the charts, that tau is equal to 0.6466, then you can say it is equal to alpha t divided by r0 squared. Okay. It's equal to alpha, which is equal to 1.477. multiplied by 10 to the minus 7 multiplied by t. And again, just look at the sketch. It will show you that the radius is 0.15 square, and the result of that would be equal to, again, 98,517 seconds. What I like about the Heisler charts is that it is so easy to make a reading error from the tables or to make a finger error when you do a calc. So it only takes 1 minute to check the chart and see if your order of magnitude of calculation is approximately right. So that can guide you so that you know, oh, I've made a mistake somewhere. There was a question somewhere?
Okay, I think it's fine. I thought we were supposed to get the correct answer there, but I can see you still use that value, then it's fine.
Which value?
The 0.882.
Yes.
I did it with
Yes.
0.29.
Yes, okay, yeah, so I've still used that non-dimensionalized temperature. So the question was, I've used that non-dimensionalized temperature of 0.8, where maybe I've made a calculation, it should be 0.2 something, but you can just go and correct it.
The tau value of less than 0.2.
What happens if?
You calculated the tau value of 0.2, less than 0.2.
Yes, so the question is, what happens when you calculate that tau is now less than 0.2? Then it means that that day I was very angry at you when I compiled the test and exam, and you will have to go and calculate quite a few numbers of tau and A1. That is what it means. Okay. However, you've all passed mathematics. So if you do the first term and you tell me, you know you should also do the rest, then I'll be happy. Okay. Question?
I know we calculated that bulk temperature because of the fact that there was the difference.
Yeah.
And you said that because we're dealing with something that doesn't change very much, the properties doesn't change very much over time, so our error percentage is small.
Yeah.
What if we were dealing with a substance that its properties change dramatically? Because those properties are changing linearly with temperature, but the temperature isn't changing linearly.
Yes.
The problem. So would that be
Okay, so the question was, let's suppose we deal with a body where the properties were quite dependent on temperature. Are there such bodies? The answer is yes. If you typically look at composite materials, then that is a good example. However, this is a case where you first have to crawl before you can start walking. So we start simple and we move it up, making it more complicated and giving you more accurate tools. In many cases, ladies and gentlemen, okay, for those of you, you'll see in many cases, and specifically in the next part of the section also, the analytical solutions are not available. So those of you who want to go and win a Fields Medal, you know what the Fields Medal is? There's not a Nobel Prize for mathematics. There's a Nobel Prize for physics and chemistry and medicine, but not for mathematics. So the Nobel Prize for mathematics is the Fields Medal. So there are lots of opportunities for you to actually get the analytical solutions for us, where K is, for example, can be taken into consideration as a function of temperature. We do not have those solutions yet. And that is one of the reasons why you do the course, the MKM course now, where you're going to discretize it and when you can solve it numerically. Okay. I see we are out of time. I actually hope that we could start with paragraph 4.3, but since we only have 2 minutes left, thank you very much, and that's the end of the lecture.